All right. So we're going to start with 4.6. If you were having trouble with multiplying two binomials together before, this should hopefully clear that up a little bit. This is kind of like the other method to do that. And after you know both methods, like hopefully things will be a little bit less chaotic. So this method, this is called the FOIL method. And this method works. This method works. You ever see the movie called Slapshot? So nobody ever remembers that movie, but in the movie Slapshot, the goons, the brother goons, there's a scene where they're putting foil on their knuckles, and the boss is like, "What are you guys doing?" And they're like, "Boss, we're putting on the foil." I even played that video clip for a class once, and they all looked at me like I was crazy. Yeah, I was like, "No, guys, I'm serious. It's funny." And they were like, "Yeah, just get to the math, dude. Shut up." Yeah, okay. So the FOIL method basically helps us to organize our multiplication. So the FOIL basically spells out F is for the first terms, O is for the outer terms, I is for the inner terms, and L is for the last terms. And so let me just show you how that works. So when I first start doing this, I write out the word FOIL, F-O-I-L, in big letters with plenty of space out in between. And I write it slightly above where I'm going to write my multiplication. So the F stands for the first terms in each binomial. And so this little arc from my x to my x, that's my F multiplication right there. So that gives me x squared. Right? And so it's F means multiply the first two terms, or the first terms in each binomial. Right? And so when I do the FOIL, especially when I'm learning to do it, I like to draw visual arcs. And that way I can see what I've multiplied already and when I'm done with this. So the next one will be my outer two terms. And by outer, I mean the outermost terms in either binomial, right? You can see it's x times positive 4 here. So the outermost terms. Okay. So that gives me plus 4x. And if it's positive or negative, don't forget to write the sign in between, because we're just going to add these all together when we're done. Now the next one, I'll draw the different color here. The innermost terms, I have 5 times x, right? The 2 on the inner, on the inside. So that gives me plus 5x. And then finally, the last multiplication is the last two terms in each binomial. 5 times 4. And so this is kind of like the standard way that most of my FOILs looked when I was learning the method. Eventually, you know, you'll stop drawing the arcs and everything like that. And actually, you know, even to this day when I'm doing it on my own, I still draw the arcs. But, you know, kind of get comfortable on the way this looks, right? When you do a FOIL, if you're using binomials, there should be 2 arcs off the first term in the first binomial and 2 arcs off the second term in the first binomial, right? There should be 4 arcs total, 1 for each letter in the word FOIL. And so after we make sure that we've hit every letter in the word FOIL, we just combine our terms. And so for this one, my x squared stays the same because there's no like terms, but my 2 terms in the middle are like, so I can add those together. 4x plus 5x gives me 9, plus 9x. And then my 20 still just drops straight down. Yeah, so it's not too bad, you know, and as long as you sort of memorize how this is set up, you know, the rest comes kind of naturally. Just remember to write out FOIL, right? And just remember, first, outer, inner, last. You know, and all you need to do is just make sure that every term here is multiplied by every term here. That's all we're doing. So this is, they have it in your chapter outlined like this. This is a good way to do it, even though they don't quite draw their arcs like I do. You know, you can draw your arcs however they make sense to you.
That one looked confusing.
Yeah, for me too, right? For this one, it's awesome because you know, even if there's an extra term in this first binomial, it's still the same thing. And so if we had like a plus y back here, there'd just be two more arcs going from y to each term right here.
And I think the first started getting lost is when we added it 2 and 3.
Oh, when we started putting coefficients on the first terms? Yeah. When they do that, you can still use the FOIL method for that. That still works just fine. Yeah. And so something we'll recognize real quick here. And like I said, this pattern is going to come up later, so don't worry about it for now. I'm just kind of pointing it out so you see what's going on. This number right here is the product of these two numbers. That's always going to happen when you don't have coefficients out front, when it's basic binomials. And then this number right here, 9, that's going to be the sum of those two numbers. That's the pattern. It'll come up later. This chapter, it's not very important, but later when we're factoring, it will be. But if you recognize that pattern also, and you notice these are just two simple binomials and there's no coefficients, you can eventually, not right now because we're learning the FOIL method, but eventually, I'm not going to require that you show me the FOIL method anymore. Eventually, you can look at these two and know exactly what this will be by just saying, well, 5 plus 4 is 9, so 9x must be the middle term. 5 times 4 is 20, so 20 must be the end term. I'm done. I don't need to FOIL. Eventually. Right now, though, you're definitely going to want to use the FOIL, but eventually you'll be able to see that pattern and just move ahead without FOILing. Okay. So let's do some examples here. So here's another example, right? When I say basic, easy binomials, this one is not one of those, right? Because we have an x squared term. And so, like, you know, this is slightly outside of the realm of basic binomials. But we still use FOIL. Okay, so for I'll write out FOIL here, F-O-I-L. And then I'll draw an arc for my first multiplication, which is the first two terms, or the first term in each binomial. So I have x times x squared, and that gives me x cubed. So the next thing I want to do, after I've done the first two terms, I go to the outermost terms for the O. That's this big arc right here. That gives me a plus 5x. And so now that I've drawn an arc from this first term to each term in the second binomial, now I start with this next term. So now I have my I multiplication. I stands for your innermost terms. So I have 8 times x squared here. And then finally, I have my last term. So I draw my final arc, 8 times 5. That gives me a plus 40. And so now we combine any like terms, which as we kind of like look at these, we can see that none of these terms are like. But just because we're picky mathematicians, we want to arrange these in descending order. And so I want to go from highest degree to lowest degree. I won't mark you off on an exam if you don't do this, but I will smile if you do it. So I go from my x cubed term down to my x squared term. So I have plus 8x squared. Then I drop down to my just plain old x term, plus 5x, plus 40. And so notice here like how these were not simple binomials, and notice how the pattern did not hold in the middle here. And so we're used to having, right, these two numbers still multiplied to give us our constant term, but we didn't really have a middle term, so it doesn't make sense that those two numbers added to get that one. So that's how things break down when it's not a simple binomial anymore. So let's go to this next example. This one is a simple binomial.
So that pattern is only going to work for the simple.
Only, yeah, and I call them simple. That's my own sort of, you know, simple or basic or you know, just whatever. And yeah, it means it looks like
Any
this.
of them doesn't have exponents in it?
Yeah, if it's got an exponent in it, if it's got a coefficient, right? Like the ones that you said were a little weird, the ones like, say, like 2x minus 5, those ones are not simple anymore. It has to have a single x and then plus or minus an integer, okay. And then it's simple.
All right.
Yeah. Okay, so here's another example of simple. And in the end, like, you know, like this is what we'll be able to do eventually. You'll be able to look at this and you'll be able to say, well, x squared is going to be the first term like always. The middle term is going to be the sum of these two. So this is going to be plus 11x. And then the last term will be the product of those two. So it should be plus 28. So let's go ahead and FOIL this and see if our pattern holds. Okay, so I write out my FOIL, F-O-I-L. And then I do my first multiplication, meaning the first term in each binomial. That gives me x squared. Then I go to the outermost terms, all the way to the edges. So that's plus 4x. I do my inner term again, 7 times x. And then finally, I do my L multiplication, the last term in each binomial. 7 times 4 gives me plus 28. And if we just take a look at this real quick, we can see, yeah, the pattern's going to hold here when we combine like terms. Okay, so for this next one, before we get to some ugly stuff soon, for this next one, let's have you try this one out, right? So that when you get to that homework assignment, it's not like that brutal, like, what do I do now? So just, and you guys at home, go ahead and pause the video and take some time to work this out. Or just do it while we're sitting here in silence.
Right away, my brain's going, oh, there's pluses and minuses in here.
Yeah, actually, I think I might have given you sort of a weird one to start out with because I don't think we've dealt with a minus yet. Nope. But just remember, the minus sign goes along with anything it's multiplied by. No?
end up with like y2 minus 6y. All my minuses mess me up.
Okay, so let's go through it one step at a time here.
Okay.
So for your f multiplication, you want to hit the first the first term in each binomial, so you get y squared.
Correct.
Now for your o multiplication, you want to do the outermost terms.
Yep.
So I should have y times -2 gives me -2y.
Okay.
Now I have my inner multiplication, the innermost terms, and that should give me plus 3y. And then finally, for my last multiplication, I should get -6.
Yep.
Is that what you got?
Yep.
Nicely done. So now when we put it all together, let's take a look at what we have. We have y squared plus 1y minus 6. Now let's take a look at our pattern. And this is an interesting one. This is the first time we've had some negative numbers in our pattern. And we see that the pattern still holds, right? So our last constant term, that's a -6.
Okay.
Right? -6 is -2 times +3. And when we think about our sum in the middle, since one of these is a negative number, we're actually thinking about a difference.
I would bring down -y or positive y, or negative y with a y. Okay.
And remember, if you reach the step where you're at the end and you're like, well, I'm not sure if I did that right or not. If they're simple binomials, just say, well, 3 minus 2 is a positive 1. That's what I have on my middle term. And then you can say 3 times -2 is a -6. That's what I got on my end term, so I must be correct. Okay, we're going to skip one example and go on to part E here. Okay, so we're going to do example E, and this is kind of just to show you that this still works, even though this does not look like our normal examples. We usually like to start with x in our binomials, but it doesn't change anything because we started with the other number. That doesn't matter. So I just write out my FOIL like always, F-O-I-L. So for my F multiplication, it's the first term in each binomial. Right? And so this gives me 3 times 7, that's 21. Now for my O multiplication, the outermost terms. Yeah, let's see, now it's -15x cubed. Yeah. This is going to be an ugly one. Now I move on to my inner multiplication. -4x times 7, that gives me -28x. And then finally we have the last multiplication. What should I get for the last multiplication?
Sorry, probably 25.
Don't worry about it. Well, what should I get for the last multiplication?
25x squared.
Almost. So our coefficients are -4 and -5. What do those two multiplied together give us?
Sorry,
20. There you go. But it's since they're both negative, we get a positive though.
Oh,
right? They cancel each other out. Yeah. So we have plus.
Things happen to a bad person.
Yes.
Positive things.
There you go. Yeah. So we get plus 20, and then we have an x here and 3 x's here. So how many x's do we get when we multiply them together?
4.
4. Yeah.
Never mind, answered my own question.
Okay, and then, you know, I would completely accept this answer, but just because I don't like the way it looks, I'm just going to rewrite it in descending order to call it good. So that ends up as 20x to the 4th minus 15x to the 3rd minus 28x plus 21. And so just so that you know what it looks like, maybe I'll just do a quick example when I have more than 2 terms in the other binomial. So you can see, like, you know, it's not FOIL quite anymore because there's more letters now, but it's the same concept, right? You can see the arcs are very similar. So suppose I wanted to multiply together x plus y plus 5, and I wanted to multiply that by x plus 3. Well, to do that, I would just start with my x, right? Multiply by the first term to give me x squared, multiply by the second term to give me 3x. Then I just move on. Oh, sorry, I'm going too fast.
Okay, I'm writing.
So since I multiplied my first term by every term in the other binomial, now I start with my second term. So now I draw arcs from y to x to give me plus xy, and then I draw an arc to 3 to give me plus 3y. And so this is the only step that really changes with this third term, is that I have 2 more arcs to draw now. It makes my paper look a little more chaotic. And so now I go from the last term, 5, yeah, back to x, so I get plus 5x, and then back to this last term, plus 15. Okay, so let's go to multiplying sums and differences. So the first thing we're going to go over here, and I should say first, so we just went over FOIL, which is considered a special product, but really it's just a way to organize your work. What we're getting into now are considered more special products. In other words, they're like formulas for multiplying things together. So first thing we're going to go over is I'm going to show you why we get this special product. So if I take 2 arbitrary things and multiply them together when they're set up like this, let's just see what happens. So I write out my FOIL, F-O-I-L. My first multiplication is going to give me a times a. So that gives me a squared. My outer multiplication, I do my outermost terms. That's going to give me a plus b times a. Now the innermost, because it's set up this way, always gives me a negative b times a. And that's crucial to why this formula works the way it does. And then I'll do my last multiplication, negative b times positive b. That gives me negative b squared. So I take a look at what I just got, and I combine all like terms. And we can see these two terms in the middle, they're always going to cancel. Because of the way this is set up, with a negative and a positive like this, you're always going to have positive b times a, negative b times a, and they're always going to cancel. And so that results in a squared minus b squared. So now let's do that same exact thing, but we'll replace those. We'll replace a and b with actual values, right? And we'll see why this works with regular values too. So once again, I have my first multiplication, which is just going to give me x squared. Then I have my outer multiplication, which is going to give me negative 5x. My inner multiplication, which gives me positive 5x, just like I thought it would. And then finally, my last multiplication gives me negative 25. We can see here these middle terms cross out just like they did with the above example. And this gives me x squared minus 25. So this is one of the most common special products that you're going to run into. I love putting this on exams because if you don't see it, you can still absolutely solve the problem. But if you do see it, it can knock like 80% of the work off the problem. And just kind of notice like what we did here, right? This first line, we used all very general, just A's and B's, right? So that we could work out a formula for how this is always going to work. In the second line, we did it with a real example, and we see that our formula is valid, right? Over here, I have x plus 5. So my x was equal to a, and my 5 was equal to b, right? And so just real quick, if I wanted to use this on a different example, suppose I had x plus 3 times x minus 3. And I recognize, I say, this is a difference of squares, because it's set up exactly like this, right? So I can say, well, the formula says this is a squared minus b squared. Now that we've gone over the special product, you don't need to FOIL it. You don't need to show any work. You could just say this is equal to x squared minus 9. Right? You could skip all that other stuff, right? We never have to do this part again on a difference of squares if we don't want to, right? Now I can say it's rare that everybody just memorizes all the special products right away, but it will start to sink in, and if you memorize especially this one, it will help you a lot. The one that we're going to go over in a little bit, perfect square, trinomials, and things like that, that's less useful. This one pops up everywhere, everywhere. All right, so here's the official definition in the book. You can always reference that if you need to, but it's called a difference of squares. And just like I've been saying so far, right now we're taking this left side and we're turning it into this right side, but eventually we'll go the other direction. and when we do that, this is also a special product that helps to remember. Whenever you notice that you have one square minus another square, you can automatically set them up like this. Okay, so let's try this out a couple times. All right, I'll just write the formula over on the side here. I'll write it down here so I don't have to write it a bunch of times. A plus b times a minus b equals a squared minus b squared. If you're going to remember just one special product, this is the one to remember. Okay, so the first step to implementing this is just to make sure that you have a difference of squares. Right? The only thing that matters with a difference of squares is that I have, that my binomials have the same first term, the same last term, and a plus and a minus in the middle. Right? One has to be plus, one has to be minus. That's what makes this work, is that it looks like this general thing right here. Okay, now that we recognized that it looks like the general thing, we just say, well, a squared minus b squared. We can just fill in this formula, basically. A is equal to x, so I have x squared here. B is equal to 4, right? So I have minus 16. Done. Yeah, and before we move on here, let's just notice that because these binomials are simple, our pattern still follows. And so this last term, negative 16, it's still the product of these two constant terms. The middle term, which we don't write because it's 0x, right? The coefficient on that term is still the sum of these two constants, right? They're opposite, so we get a 0x in the middle. All right, so the pattern still holds with simple binomials. Okay, so let's try this next example. This one's a little less straightforward, but that's okay. And sometimes it helps people, like, when they're first filling out these special products, to label what each variable is. And so, like, I notice this is a difference of squares. So I can say, well, a equals 5, b equals 2w. And then that makes it a little easier to fill in your formula, right? A squared, okay, 5 squared, minus b squared, okay, 2w in parentheses squared. Yeah, right, and yeah, it's just, when you fill it out like this, you can really just kind of enter it in exactly and then work out the math in a second. So when I work out 5 squared, that gives me 25. And then 2w squared, that is 4w squared. Okay. This is a good example of when this, because it makes things really easy, right? And so what's my a equal to in this example, number C? Perfect. 3a to the 4th. And then what's b equal to? B is just 5. Yeah, remember that the sign doesn't go along with B. Yeah. What do you mean? Oh, yeah, so with this one, right, I have a squared, so I'm just careful about it, and I put it all in parentheses. A squared minus b squared. Now I just got to do the math. So let's see now, what is 3a to the 4th squared? Remember how we do this. When we have a square on the outside, we distribute it to each term on the inside. Okay, so I square my 3 first, and that gives me 9. And then if I square a to the fourth, what do I get? This is, what rule is this? This is a rule on the first page of this, the last rule on the first page. Power of a power rule.
So we're just trying to, right?
Yeah, you just multiply the exponents, yeah. And so a to the fourth, exactly.
So,
A to the eighth.
okay.
Good. Okay. And then we know how to square 5. It's just 25. You could put the 5 in parentheses if you wanted to. That would be fine. Okay. And now I just want to point out, be careful on this step right here. A lot of students are really tempted to turn this into positive 25, but because there's no parentheses around the negative, the square does not apply to the negative. It only applies to the 5. So that stays as a negative 25. Okay. All right, so that is kind of the basics of difference of squares. Like I said, that one is a very important one. Even though you'll have to do other types on your homework, that one is like the chief importance. So let's do that same kind of technique that we just did for difference of squares, but we'll do it with a perfect square instead. Right, and so instead of two binomials with opposite signs in the middle, this is the same binomial multiplied together twice. I know, that's weird, right? So when you write this out, right, it's just squared means this times this. So we say, well, this is equal to a plus b times a plus b. Okay, so let's FOIL this beast out. F-O-I-L.
Really like all of this math logic.
I don't know. I often think about that myself. Like, you know, the guys who first figured out how to multiply these things together, like, did they have to come up with FOIL, or were they just like, oh, well, we get it?
We're just gonna write this down.
Yeah. And they're like, well, we created it, so we don't need FOIL, right? Was FOIL invented in the last? Well, obviously, since FOIL was invented,
Yes.
they wouldn't have come up with it before then.
Even when, you know, all the greatest mathematician minds were sitting around, somebody had to go and sat there and went, we're going to mess with these people over less.
Yeah, I would believe it. I would believe it. Yeah, without a doubt. Yeah, I was just looking up the definition to something weird in the other class that I was taking, and you know, I was like, oh, and these guys two French students came up with this word from Latin that means this. It's a metaphor for this, and I'm just like, what?
Why do you even need it?
Yeah, just call it an analytic function, and they're like, no, we must call it holomorphic. Yeah.
Why does everything have to be especially unicorn? Just stop. Unicorns were black. Okay? They're not bright and shiny. They're mean and they spit stuff at you.
Right? That horn was meant for stabbing. It's so funny. All right, so let's go ahead and FOIL this general thing out so that we can find a formula for what these perfect square multiplications look like. And when I keep saying perfect square, this is what I mean, right? It's something squared, and especially when it's a binomial, we will call it like a perfect square.
All right.
Okay, so I do my F multiplication. That gives me A squared. I do my O multiplication. That gives me plus AB. I do my I multiplication. That gives me plus AB again.
This is the part where I always seem to get I'm like, oh, okay, we're plusing AB, but my brain wants to do something completely different.
Does it? Yeah, you'll get used to this after a while. It takes a bit, though. And then finally, we get a plus B squared.
But what I want to do is, A squared, B squared, C squared, like alphabet.
Ah, yeah, don't do that. Yeah, when I do these examples where I replace like numbers and variables with A and B, like that's pretty much how we create formulas in a lot of mathematics, is we just say, well, what if we just said these are completely general and no matter what A and B is, this is what it comes out to. That's what they do with a lot of these. It's very useful with some stuff. So with this one, we can see the middle terms didn't cancel like they did with the difference of squares, right? And so this is a different formula. This is A squared plus 2 times AB plus B squared. And so this is the formula for a perfect square binomial. This one, you'll probably use it 10 times in the homework and then never again. Never again. No, you actually will. So next semester, you start using this one a lot more. This semester, I don't necessarily hit you with that one too much. This one, if it's on the exam, it won't be, I guess I should say, like these special products, if you don't know them at all, you can just brute force your way through everything and use the FOIL method or the distribution method. If you know a special product, it might make your problem go far more conveniently, but it won't stop you from solving it. I'm going to be honest with you, I didn't memorize any special products. In my first algebra class I took, I brute forced everything. I didn't even bother with it. It probably cost me hours of my life, but I made it through fine. I learned them the next semester and then realized what a mistake I'd made by not memorizing at least the difference of squares, because that one was everywhere, and so yeah, these, they might make it a little more tedious on an exam, but not knowing this one isn't going to kill you. Not knowing the difference of squares might get to you eventually, because that one will be on the exam. I always put the difference of squares on the exam. And a lot of times on the extra credit problem, I'll like put a difference of squares in there. And if you recognize the difference of squares in the extra credit problem, a lot of times like the work just almost goes away and it's done. But if you don't recognize it, then it's like a half hour of brute force tedium. I've put that in there in the past. So, I like to do stuff like that. So in your book, and I'm skipping ahead of it so that we can do a couple examples with this. In your book, it's got both of the formulas here. The one that we just worked out with was A plus B. There's a different formula for A minus B. Right? The only change in those two formulas is the sign right here. Yeah, it just changes the sign of the middle term. That's it. Okay, so let's go ahead and start using this formula a little bit. So I'm just gonna scroll down here and write them both out. So I have A plus B squared is equal to A squared plus 2AB plus B squared. And this one, A minus B, is equal to A squared minus 2AB plus B squared. Okay. So my first example, I have a plus sign in the middle. So I'm using the upper formula here. So all I need to do, right, I mean, these are really easy to recognize that it's going to be a perfect square. So there's not a whole lot of legwork to do here. You can just, if you need to, you can just write out the formula above. So A squared plus 2AB plus B squared. And then just fill it in. A is equal to X, B is equal to 7. So a squared becomes x squared. 2 times a times b, that becomes 2 times x times 7. And then the plus b squared, that just becomes plus 7 squared. And then we just go through and simplify things. So my x squared stays the same. Oops, here, I'll write it over here. My x squared stays the same. This middle term, 2 times x times 7, that becomes 14x. And then my last term, that just becomes plus 49. And so you can see, like, you know, that was kind of like the first time we used that, we took it really slow. That was still about equal the amount of time that it would have taken to FOIL that thing out, you know. And so those can become very useful, especially if you do a lot of these multiplications. Okay, let's try another one. This one looks a little bit weird because this isn't an integer here, but that's okay, because when we figured this formula out, we didn't specify it had to be an integer or anything like that. So we're going to plug this stuff in just how it appears. So I go ahead and I write my formula out. A squared plus 2ab plus b squared. I just recognize that a is equal to 3 little a, and b is equal to 0.4. So I just plug everything in directly, right? I'll put stuff in parentheses, right? Because that's definitely how it goes. Since a is equal to the full 3 little a, I need to put that in parentheses, right? So it's the full capital A squared. Then I have plus 2 times a, which is in parentheses, 3 little a, times b, which is 0.4. And then plus b squared, 0.4 squared. So when I square my first term, this 3 little a, I square the 3, which gives me 9, and then I square the little a. This middle term, I'm just going to punch this in my calculator. So I don't feel like doing that. So I multiply all my coefficients together, which is just 2, 3, and 0.4. So 2 times 3 times 0.4. That gives me 2.4. So I say plus 2.4 little a. Yep, just multiply them all together, right? Because everything's multiplication here, and so I have 2 times 3 times a times 0.4. And remember, multiplication is commutative. So we can rearrange anything we want. So I just multiply all the numbers together, leave the variable. And then finally, I'm going to punch this last one in my calculator because squaring decimals is a weird operation to me. So I'm going to square 0.04, and I get out a positive 0.16. And that's it, we're done.
I missed one little, I was writing, I wrote down one thing wrong. I was like, why did I miss something? Oh, you wrote it down. It's fine. Other than that, you're fine.
And so just note, like, with these decimals, this is not like a typical polynomial problem. We usually use whole numbers or integers or whatever. But just because things are decimals doesn't mean a whole lot changes. Okay, and so let's do let's do this ugly one down here, since we're starting to. I think we're going to end up running into. This is good that I have more time for tomorrow. These lectures here are some of the more like the learning curve on this week and next week is just super steep. Like, we're already going over some of the more difficult stuff, but yeah, it just kind of like ramps up here a little bit. So it's good to like take our time. Okay, so let's try this last example. We'll skip example C because that's basic. We've done a few of those already. Let's do example D. So example D, it's still a perfect square. I've got a negative sign in the middle though, so it's the other formula. So I go ahead and I write out my formula. A squared minus 2 times A times B plus B squared.
Suppose if you have plus B squared at the end, even if it's negative or positive.
Yes. Yeah, and that's because if you sort of imagine these two things written out right next to each other, your L multiplication on the FOIL will always be negative 3x times negative 3x, and which gives you a positive. So no matter what that last term is, positive or negative, the square gives you a positive. Okay, so now since this one's a little bit weird and my terms are not so easy, I'm definitely going to write this one out as A equals 5x and B equals 3x to the fourth. Now remember that negative sign doesn't come with the B. So now I just substitute everything in.
We're leaving the square out.
Yes, yeah, because this square was on the outside of the parentheses. And so that's the square that goes on the, right, that's like this little guy here in the formula.
Okay.
Yeah, so that guy kind of just goes away after we're done here. Okay, so I have my capital A equals 5x, so I'm going to put it in parentheses, and I have 5x squared. Then I have negative 2 times A times B, so that gives me negative 2 times A, which is 5x, times B, which is 3x to the fourth. And then I have plus b squared, which is in parentheses 3x to the fourth squared. You can see why these parentheses become really important, right? Like, obviously if you didn't put parentheses on this first term, you'd be really tempted not to square that 5, but that has to happen. Okay, so now take it one step at a time and just go through and write out what each of these terms are. So 5x squared, what should that get me? Yeah, and so now that I've kind of like I've plugged everything into the equation, now I want to simplify everything. And so
10x.
Careful.
Oh, I'm sorry.
What's 5 squared? I know. Right? You see 2 and 5 and you just jump on it. It's okay. That is like I don't expect you guys to like transition to exponents that quickly. It's okay to like have that old training of multiplication like slip into problems. It happens to me all the time. So we square the 5, right, which gives us 25. And then we square the x, which just gives us x squared. So on this next term, first I take a look at all the coefficients. I have 5, 3, and negative 2. If I multiply all those together, I get 5 times 3 is 15, times negative 2 is negative 30, right? So I have negative 30, and then the variables are x and x to the 4th. Since I'm just multiplying like bases together, I just add their exponents. So that gives me an x to the 5th. That's okay. It's okay. We got to train ourselves, right? So for the last term, right, I distribute the square to the 3. And that gives me 3 times 3, which is 9. And then I distribute the square to the x to the 4th. What does that give me? Careful. This is a different situation, right? We're not just multiplying like bases. We're taking an exponent to another exponent. So this one's a different rule. Yes, good, good. Yeah. Now once you start memorizing those rules, it'll just fall into place eventually. Yeah. Yeah, so that was it, right? That was that could have been a little uglier if we hadn't used the special product. And in the end, we'd probably want to write it in decreasing order as 9x to the 8th minus 30x to the 5th plus 25x squared. But like I said, I wouldn't take any points off for that on an exam. Okay, so now let's take a look at probably one of the most common mistakes that we have in this class. This means not equals, this little sign right here. So this is never, well, I should not say never the case. In general, this is not the case, right? And so you don't distribute this 2 to each one of these. You have to write this out like we just did. A plus B times A plus B, right? This is a FOIL, not a distribution. Right? And so a lot of people, this is what they want to do. They'll say x plus 3 squared. Oh, this is equal to x squared plus 3 squared. No. Bad. Yeah, we don't want to do that. That's a really common mistake. If you do that, it's okay. Like, I understand because everybody makes that mistake. But that's not the way it is, right? We got to write this out in its long form like this, or just remember the special product or, whatever. But yeah. And you might be tempted because if we have this 3x squared, in this situation you do distribute because this is multiplication in here. So then we have 3 squared x squared. But this situation is different because of the plus sign in the middle. We have to FOIL it. Okay, so yeah, 3 times x squared, that's easy. You just distribute. 3 plus x squared, then you have to FOIL. Okay. And it, like to kind of help inform yourself, like so that you don't make that mistake, you might write them both out sort of the longhand just to check, right? Okay, so we actually don't have time to go over the entire next lecture. So maybe we will, let's see now. You don't get out that easy, Marcano. Just chill. Just chill out there, Ramjet. maybe I'll just explain the concept, sort of, just so we can warm your head up. Yeah, so the concept of, just forget this, evaluating polynomials. When we talk about multivariate polynomials, we mean there's like, 4x squared y, right? When we do things with multivariate polynomials, we do them pretty much the same as when we do them with single variate. We just keep the variables separate, right? And so if I want to multiply 4x squared y by 3x to the 4th y squared, I just multiply the coefficients together to get 12, multiply the x's together to get, what should I get here?
We're
Sorry, that was rude. I was pulling you out of your zone.
I'm watching. Sorry.
Okay, so right,
No.
so we have like bases.
Right. X and X, and then you've got 8. Okay, yeah.
Not 8.
Oh, we're adding on this one.
Where yeah, exactly. Yeah, remember, yeah, when you have two bases, then you add. Yes, we have x to the 6th, right? And we do the same thing with these. We add their exponents.
Y3.
Good. Y to the 3rd. Yeah, exactly. And so that's it, right? That's multivariate for you. There's going to be a few more things to remember, but we'll go over them in the lecture. When you add multivariate things together, they have to have the exact same variable factors. And so I could not add this with something that looks very similar. If I wanted to add this to 12x to the 5th, y to the 3rd, I can't do that, because I have 6 x's here and 5 here. So the variable factors are slightly different. What I could add this with, the only thing I could add this with is another term. Let's say it's 3x to the 6th, y to the 3rd. I can add these two together, right? These two are like, the other one is not, because it has just a slight difference in variable factors.
Oh, okay.
Yeah, and so that's it, right? Just like how we can't add a squared term to a cubed term because they differ by just 1, we can't add this term to this term because their x's differ by just 1. And so it's, the variables have to be exactly the same, otherwise it doesn't work. And so we just add these two together to get 15x to the 6th, y to the 3rd, and we'd have to just leave this one hanging out here, 12x to the 5th, y to the 3rd. So that's what we'll be working on tomorrow, and I'll put the lecture up.
Yes.
Yeah.
Yeah.
Yeah, so any questions about all that wonderful stuff we went over today?
No, I think that I just need to memorize I always mix up which is which.
Right?
Like I'll get going, I'll be like, no.
Oh, you mean the rules?
Yeah, I always mix
Yeah.
the rules.
Yeah.
Always mix the rules.
Yeah, and I,
Answer.
You could definitely use like a little 3x5 note card when you do your homework and just have the rules specifically on there. And just like these general parts, the part that says a to the m raised to the a to the n is plus. That's all you really need on that note card.
I need to, because I use this, and then I'll have this, and I'll have my homework, and I'll have my book, and I'm like, wait, what was my exam?
One thing, if you absolutely forget about it and you're like, darn it, I forgot what the rule was and I'm in an exam and I can't just pull out my book, right? We can figure out what the rule is by doing a couple test cases, right? And so I'm going to say, well, what's the rule if I have x cubed, let's say squared, right? And you say, I don't know if I'm supposed to add these or if I'm supposed to multiply these. I'm not sure. Write out the definition of squared. This is equal to x cubed times x cubed, right? And then you know it's addition. Or if you're still not sure it's addition, keep writing out that definition. Say, well, this is equal to x times x times x times x times x times x. And then you can say, well, obviously this is 6 x's in a row. This must be equal to x to the 6th. And so doing little test cases like that when you're in an emergency jam, that's all good. And that's actually highly recommended in math. Like knowing how to do those little test cases is really kind of the key to being, to checking your work when you're not sure what comes next. Yeah. And you can do, with the other rules, you can do the same thing. And so suppose I have x to the third over x squared. Well, if I just write these out longhand, I have x, x, and x over x and x. I cancel two things, and I can see this is equal to x to the 1. In other words, x to the 3 minus 2. And so all those rules can be written out in like a very basic form, and if you remember the more basic rules, then you can remember the slightly more complex rules. And that's definitely a good thing to be able to do in math. And I'm pretty sure all these exponent rules can be kind of just written out in this way so that you can slowly say, okay, let me write out x, let me write out all the x's and see what happens. Okay? All right, so that's it for today. Make sure on your homework tonight, don't start chapter 4.7 because we didn't do any of that.
No.
and it will drive you crazy. So
no, I still have like 3 that I need